we are going to continue our discussion on different regions in the complex plane and their topological and geometrical properties. And of course, if a set is given, what is the relationship between a set and a given point? Now, this discussion of different regions in the complex plane is going to help us in exploring different properties of complex functions, for example, their limit properties, their continuity, their differentiability, and other properties. Let's begin with our first definition. What is an open set? Now, a set is called an open set if every point of S is an interior point of S. Okay, so for example, consider these two sets. Let's call it S1 and let's call it S2. Now, according to the definition, if I choose any point of the set and if it is interior point, then, and if I choose every point of the set and if it is interior, then we say that the set is open. So for example, in the case of S1, let's choose this point P1. Now, we know that a point is interior if there exists an epsilon neighborhood of that point which is contained in that set. Now, in this case, we can easily see that there exists the following epsilon neighborhood of this point P1 which is contained in this set S1. Now, similarly, we can choose a point very, very close to this boundary, and still we are able to find a very tiny epsilon neighborhood of this point which is contained in the set S1. But if we choose a point at the boundary, then whatever neighborhood we choose for this point, this neighborhood is never going to be contained in the set S1. But this point at the boundary is not included in the set S1 because the boundary is dashed and it is not continuous. So this means that the boundary is not included. So in other words, we can say that for every point of this set S1, there exists an epsilon neighborhood which is contained in the set S1, or we can say that every point of this set S1 is an interior point of S1. So we can say that this is S1 is open. Now let's consider this set S2. Now on the same lines, whenever I will choose a point in this blue region, I'll be able to find a very small epsilon neighborhood of that point which is contained in this set S2. But now, what is the difference between S1 and S2? Now the points of the boundary are also included in the set S2. So in other words, if I choose a point at the boundary, let's call it Q, and if I choose any neighborhood of this Q, now this neighborhood is not going to be contained in S2. So in other words, this Q is not interior point. Q belongs to S2, but Q is not an interior point. So in other words, we can say that this set is not open. Now, a set is open. Somehow we can say that a set is open if the boundary is open. The boundary is not included. And if the boundary is included, we call this set closed set. So precisely, a set is closed if it contains all its boundary points. So what are the boundary points? So recall that a point is a boundary point if it is not an interior point, not an exterior point. So in other words, in this example of S1, these points are the boundary points. Okay, so all of these points are the boundary points. Now we can easily see that these boundary points are not included in S1. So we can say that this set is not closed. And in the case of S2, we can easily see that all the boundary points are included in S2. So this set is closed. Now let's continue our discussion. We have this definition of accumulation point. It is also known as limit point. So what is limit point or accumulation point? A point Z0 is called an accumulation point of a set S if every deleted neighborhood of Z0 contains at least one point of S. So let's start with this set S and take a point Z0. Now we want to see that if this Z0 is accumulation point of S or not. Now the definition says that if every deleted neighborhood of Z0 contains at least one point of S, then this Z0 is accumulation point. Now, note that whatever deleted neighborhood of Z0 I will choose, it will always going to contain some points of S. Okay, so deleted neighborhood means a disk of some radius with center at Z0, but Z0 is not included in that disk. So this is deleted neighborhood of Z0. So now in this case, I can also consider the following deleted neighborhood of Z0. Now this deleted neighborhood is also going to contain some points of S. So we can say that this point Z0 is accumulation point. Okay, so this Z0 is accumulation point. Now let's choose another point. So for example, a point outside this set S, let's call it P. Now is this point P an accumulation point of this set S? Okay. So the condition is every deleted neighborhood should contain more elements of S. Now if I choose the following neighborhood, now this deleted neighborhood, here P is not included, deleted neighborhood does not contain any element of S. So we can say that P is not accumulation point. Now once again, remember, the condition is that every deleted neighborhood should contain at least one point of S. So now we have found one neighborhood which does not contain any point of S. So this condition is not satisfied. So we can say that P is not accumulation point. Now let's choose another example. Let's consider this point Q. This point Q is at the boundary. Now if I choose in neighborhood, a deleted neighborhood of this point Q, now this deleted neighborhood is always going to contain points of S, because some part of this deleted neighborhood is always going to be inside this S. So how bigger or how smaller neighborhood you are going to choose, this neighborhood is always going to contain some points of S. So in other words, we can say that this point Q, which is at the boundary of this set S, is an accumulation point. Now we can easily observe that the boundary is dashed. In other words, the boundary is not included. So this part of the boundary is not included in the set S. So the point Q does not belong to S, but Q is accumulation point. So it is not necessary that for an accumulation point that it is a member of the set. So similarly, we can also observe that every point at the boundary is an accumulation point. Now what is the relationship between an accumulation point and a closed set? So a set, if a set is closed, then it contains all its accumulation point. Now we are going to use this condition to check whether a set is closed or not. Another definition is closure of a set. Now if a set is given, it may or may not be closed. But we can ask the following question: can we find the smallest closed set containing the given set? Okay, so the answer is yes, we can do that, and the answer is finding the closure of that set. So the closure of a set S is the smallest closed set containing the set S. And how to construct the closure of the set? The procedure is very simple. You take all the points of S, all points in the set S, together with the boundary points. So you take all the points of the set S and its boundary points, you take union of them, and you get the closure of that set S. So for example, consider the set S given as set of all complex numbers such that the modulus of these complex numbers is less than 1. Now we know that this set S is basically this open disk. Now we can easily see that this set S is not closed because the boundary points are not included in this case. But we can take the union of this set S with all its boundary points, and we can construct the closure. Okay, so what is the closure of S? Okay, so closure of S is going to be equal to closure of S is given by the set of all complex numbers such that the modulus is less than or equal to 1. So when we include this equality, then this will include all the points at the boundary. So in other words, the closure of this set S becomes the following closed set. Now this is the smallest closed set containing the set S. Now there are some sets which are neither open nor closed. So one of them is this punctured disk. Now this is punctured, in other words, the center is not included in the disk and the boundary is included. Okay. Now why this is not open? So the set is not open because these points at the boundary are not interior points, and according to the definition, a set is open if every point of the set is an interior point. Now the points at the boundary are not the interior points, so that's why we can say that this set is not open. Now let's see why the set is not closed. Now according to the fact that we just observed, if a set is closed, then it must contain all its accumulation point. And we can see that this point Z0, which is at the center, this Z0 is in fact accumulation point of this set, let's say S. Now why this is an accumulation point? Because every punctured neighborhood of this Z0 contains elements of S. So Z0 is accumulation point. So Z0 is accumulation point, but it is not contained in the set S, and so the set is not closed, because if it is closed, then it contains all its accumulation points. So the set S is not closed. So there are many other examples where the sets are neither open nor closed. Similarly, we can find examples which are both open as well as closed. Now consider the entire complex plane. Now the entire complex plane is open because every point of this complex plane is an interior point. Take any point and we can easily find a neighborhood of that point which is contained in the plane. So it is open. Now let's see why it is not closed, because there is no boundary. So the condition is a set is closed if it contains all its boundary points. Since there is no boundary, so by definition it is also closed. And there are many other examples of sets which are both open as well as closed. Now we learnt about open sets, closed sets, and closure of a set.